Welcome to AP Chemistry at Huntington High School. Today we'll be looking at the Integrated Rate Law Practice Worksheet. So we'll be taking a look at how you go about solving the different things on this worksheet. Now, before we get into the actual questions, I want to take a quick look at an overview. When we have integrated rate law, remember we're looking at concentration versus time data. And they're not asking about us about rate. They're asking about what order it is or what the slope is and so on. There's a variety of things we can calculate here with integrated rate law. But it really starts with determining is it zero order, first order, or second order for the process we're looking at. And remember, it's going to be one of the three. Now, as a quick reminder, on the AP constant sheet, these two equations are given in this form. They're just not in their y equals mx plus b form. Because remember, what we're really doing here is looking for the linear relationship. If it's concentration versus time, it's linear, it's zero order. If it's concentration, or the ln of concentration versus time, the natural log, that's linear, then it's first order. And if it's the inverse or reciprocal of the concentration versus time, it's linear, it's second order. So we're really looking for the linear relationship between the concentration time data that's given, which means we need to generate basically concentration, ln of concentration, and reciprocal concentration data. And remember, in every case, whether it's zero, first, or second order, the K, the rate constant reaction, would equal the absolute value of the slope. Now, the reason why it's negative slope in zero and first order is because when you generate that graph, the linear equation goes downhill, so it's a negative slope value, and for second order, it's a positive. But if you just think of it as K as the absolute value of the slope, you'll always be able to calculate the A regardless of which order it is. Now, if it's a zero order equation, while this relationship is true, you rarely end up having to calculate data given the zero order situation. So it's much more likely that it's going to be the one that I've highlighted here that's on the AP constant sheet. And the other equation that I think is worth knowing, besides the two that are in the AP constant sheet, is really this one. Technically, we can derive any of the half order situations from the equation above it by remembering that at A sub t half-life, by definition, we are at half full concentration. So that would be 0.5 A naught. And we can actually substitute this in for the values above to generate an equation. So at AT, we're going to be half our initial concentration. So we can always do that substitution to really get our T at half-life. So you can derive this equation, but honestly, it's a relatively easy one that we've used a couple of chapters now, so it's worthwhile knowing. It's much less likely that you're going to have to calculate the K value for a second order relationship. And yes, you could remember this calculation if you wanted to, but remember, through substitution, you can actually derive this equation. So as far as the half-life reactions go, we can actually derive them if we really need to, but I think the first order half-life you'll see often enough, and it's a simple enough equation that's worth knowing. So that's just a quick overview of what we're looking at with integrated rate law. So really, our goal is it zero, first, or second order, so that we can proceed and calculate other things. Find the K, given a concentration, find the time, at a certain time, find a concentration. All those things can come after we know whether it's zero, first, or second order. Now, the first reaction we're going to look at here is the reaction listed above. We have a data table with time and concentration data. And remember, if it's time concentration data, we're either doing integrated rate law or we're calculating rate. And you'll notice first question is zero, first, or second order, so we know we're doing an integrated rate law problem. Now, when you go to calculate integrated rate law, remember, we're looking for the linear relationship. Is it concentration versus time that's linear? Or is it the natural log versus time that's linear? Or is it the reciprocal log versus time that's linear? because if this one is a linear relationship, it's zero order. If the natural log is the linear relationship, it's first order. And if the reciprocal log is linear, then it's second order. So if you have time and concentration data, your first job is to actually calculate the ln of the concentration and the reciprocal of the concentration. Now at this point, you've got a couple of different options. If you've got access to a computer, you can plot these in Excel to see what linear is. If you got access to a graphing calculator, you can actually plug these data into the calculator and you can generate for these three situations, concentration versus time, ln versus time, or reciprocal versus time, you can generate data that tells you whether it's zero order. Now, I plugged into a graphing calculator and I printed out what I've got here. So when I do the linear regression of concentration versus time, it gives me the y equals mx plus b form, so I've got the slope and the y-intercept. But really what I'm doing here is I'm looking at what's going on with r squared. Now, as you know from math class, for those of you who have talked about this, and we've talked about it in chemistry as well, the closer you are to 1 for your r squared, the more linear it's going to be. So really what we do is we graph the concentration versus time, then we graph the ln of concentration versus time, and then we graph the reciprocal of the concentration versus time. And we look at which one gives us the r value closest to 1. In this case, that's right here. So that means we have a first order relationship. If the natural log versus concentration is the most linear, then that's our first order relationship. So in this particular way, we've generated data that we can use on the graphing calculator to determine what's linear. Now, if you don't have access to the graphing calculator, remember you can actually take a look at the slope for this ordered pair. So picture this and this as a y and an x value, and this as a second y and an x value. Take the change over y over change over x for those two, calculate your rise and run. You've got the slope. Do the same two things for your last data points here and compare the two slopes. If it's linear, those two calculated slopes would equal each other. So the change in y over the change in x would actually be relatively constant if it's linear. So you can do that for the first situation, then do the same thing with the natural log. This would be my y value, and once again that's at time 0, so that'd be my x value. This would be my y2, and this would be my x2. Do change in y over change in x, calculate the slope between those 2 points, and do the same thing between these 2 points and those new times. And once again, if the slope is relatively constant, then you know it's linear. And then once again do the same thing here. This would be my x1, my y1 at time 0, x1. This would be my y2 at time 2, which would be 30 seconds. Calculate the change in y over change in x there, and do the same thing here and here. And once again, compare your slopes. And you'll see, using this method, it takes a little bit longer. You're really doing 2 calculations for slopes for each situation. You can see which one has the slope that's remaining the most constant. And you'd also see that it was first order. So remember, you don't have to have a graphing calculator to do this, but certainly makes it a lot quicker. So once I've established that it's first order, by looking at which one is the most linear situation, now I'm ready to answer other questions. And one thing to keep in mind at this point, now that I've established that it's first order, the most important relationships that I'm looking at are what's happening here between these two columns. Because remember, if it's first order, that establishes, by what we looked at on the previous slide, an equation here that we can use to do various things. It also reminds us that the absolute value of the slope of that situation would be our k. If we're given a concentration at any time, we can calculate how long that took because we know what our A naught is based on the table. And if we know what our new concentration is at some time later, we know these two values, we know our K, we can solve for T. And we can also, at a given time and a given initial concentration, solve for some later time. And we can also do half order calculations. So there's a number of different things we can do here once we know it's first order. Now you'll notice, remember that was our important bit of information here. Since it was first order, that's really the key to what we're looking at. And remember, that's the data that is important here. We can first look at what is the rate constant. Remember, rate constant, and this is something you write right in on the AP test. The rate constant which is k, is going to equal the absolute value of the slope. So if we take a look up here, our slope, remember in this particular form on our calculator, our equation is in the form of y equals ax plus b. So a in our calculator here is going to be our slope. So the slope in this case is negative 0.00, and my data here has looks like varies a little bit, but it's at least 2 significant digits if we assume our time is at least to the nearest minute, or I should say to the nearest second, so it's 30 decimal point and so on. We would end up with a slope of 0.0099, and remember we're taking the absolute value of that, so k is actually going to equal here 9.9 times 10 to the negative third. So that would be my value for the slope, 9.9 times 10 to the negative third. And that's really based upon the slope of the graph in my graphing of the natural log versus time. Now, units, because you always need to have units with your rate constant. Now, in this particular case, what you really need to remember is, as a first order relationship, that means, remember, the concentrations times k equals slope. I'm trying to get the concentration times the k value is going to equal rate in our rate order expression. There is a tie between the overall rate and what the value of the units of the rate constant are. In this particular case, if we want to get molarity per second as a rate, and it's first order, that means I'm going to be multiplying as a first order relationship by an m. What would I have to multiply that by in order to get molarity over second? Well, I would need a 1 over molarity squared seconds here. So my unit in this particular case, if I've got a first order relationship and I'm taking molarity, which is a first order, it's just going to be a single m. For a first order overall reaction, it would be oh, no, that's not right. Let's back up a second here. I ran out of space, and that was messing up my thought process with this. So take a step and let's look at what's happening here. We know that we want to end up with a rate which is molarity over second. We know that overall it's first order, so that's going to give us a molarity. So what goes here? Well, I need a second on the bottom, and I need to keep that molarity. So that's going to be my value right there. I'm going to end up with inverse seconds. Now, a quick, easy way to remember this, and this is what I really should have started off with here, was the shortcut. Remember, on the bottom, you're going to have your overall order minus 1 m values. So if it's first order, 1 minus 1 is 0, you're not going to have any m's on the bottom. So if it's overall first order, there'll be no molarity on the bottom. If it's second order, there'll be 1 m on the bottom. If it's third order, there's 2 m's on the bottom. So that's really the quickest way to see it is first order, oh, no m's on the bottom. So we end up with 1 over seconds as our rate constant units. Now, next thing would be how long will it take for the concentration to reach 0.091 molar. So what we really need to do is find out what is the time going to be. So what is t in this linear graph? Remember, when we graph this data, it ends up looking like this. And this would be the ln of concentration over here and time there. So how long would it take us to reach a specific concentration? So if I know what my concentration is, I could go over, go down, and I would calculate my time. Well, I don't really have a graph generated to graphically determine what that would be, and it would be kind of a pain to do one. But if you recall, if we know this is first order, we know it follows this expression. The ln of at is going to equal negative kt plus the ln of a naught. So any first order equation has to follow that. Well, this is my slope, So I can plug in the slope for this value. This is my y-intercept, which is given as right here, negative 2.30491, and so on. They're giving me the concentration, so they're giving me this. I have an equation with one unknown, t. So once I know it's first order, yes, I can use my graphing calculator if I know what I'm doing to calculate it. But I don't really need that. I can just take the slope and the y-intercept that I've generated here, both of which can be determined from the data up above. So you don't really need a graphing calculator to do this. But if I have a graphing calculator, it quickly gives me my slope and y-intercept. I can just plug in the data here and calculate. So I know the ln of my concentration, which is 0.091, is going to equal negative k is my slope. So I'm going to plug that into my equation here. So that would be negative 9.9 times 10 to the negative 3. And remember, my units of k here were inverse seconds. Don't forget that negative there. That times t, which is my unknown, plus my y-intercept. And remember, my y-intercept is right here. It is plus negative 2.304491 and some other stuff. That should be far enough. So what I have is an equation with one unknown. Go ahead and set this equation up and solve for t, and you'll calculate how long it takes to reach that time. And in this particular case, if you do the algebra, you should get 9.3 seconds. Make sure you're actually able to do these calculations. Don't look at it and say, oh, okay, I can do that. Make sure you do the calculation and can drive it. So it's going to take 9.3 seconds to reach that particular concentration. Now, that would be an example of from a concentration calculating a time. And one thing you should always do is double check. Notice 0.091 as my concentration. 0.091 puts it somewhere between these two. Is that time somewhere between these two? Yes, it is. So that makes sense based upon my data up here. So if the concentration is here, the time should be somewhere between those two as well. So don't forget to double check if what you're doing is valid. Okay, let's take a look at the last one here. What is the half-life for this reaction? Let me clear some space here. Get rid of some of this stuff so it's easier to see. Okay, part D, what is the half-life for the reaction? Now, this is one I said you can drive the equation, but it's easier if you just know it. First order, it's 0.93 over K is going to equal the T at half-life. Well, remember, we calculated our K was 9.9 times 10 to the negative third. So that's our K value, and that was inverse seconds. So if you take 0.693 divided by K, you get your T at half-life. In this particular case, 2 sig figs, it's going to end up 70 decimal point seconds. So that would be the half-life of this reaction. So in essence, every 70 seconds, we cut our concentration by half. And once again, look at your data. Does that make sense? Well, half of 0.1 is going to be 0.05. That's going to be somewhere between those two. That's going to be somewhere between those two. Makes sense. That would be a valid half-life for the reaction. Okay, that would be problem number one. Now, problem number two, you'll notice they give us pressure and time data. Well, we kind of treat it just like we did concentration. In order for us to determine whether it's 0, first, or second order, you would graph the pressure versus time, and then you would graph the ln of the pressure versus time, and the inverse of the pressure versus time. So really in this particular case, I would look at all three of these situations and find out which one gives me the linear expression. So first you're going to look at the pressure time situation. Well, if I plug my numbers in the graphing calculator and look at pressure time, I end up with this relationship. And the key here is, that's my r squared. That's what I'm really looking at this point, is what's my r squared. Next I look at the natural log of the pressure. That would represent first order. Notice r squared here, almost 1. So it's a good guess. It's looking like it's first order, but you still need to check the last one to make sure to see if it's more linear or not. Well, it's actually 0.949. So once again, we're going to end up with a situation where we have a first order expression. Given the three graphs, the pressure versus time, the ln of the pressure versus time, and the reciprocal of the pressure versus time. The one that was most linear was the ln. So if it says justify your answer, you know it's first order. So you would put that. But how do you justify your answer? Well, you basically just say the ln of p versus time is linear. That's all you need to say. So that's how we know that it is a first order reaction. Now, the next thing we do is calculate the rate constant. Same thing we did in the previous problem. Now, in order to calculate the rate constant, first off, you need to realize that it's a first order relationship, and that first order relationship has a slope right here of negative 4.9 and then other points times 10 to the negative fourth. Well, remember, the absolute value of that slope is going to be our k value. So k is going to equal the absolute value of the slope, which in this case is the absolute value of negative 4.9. So it's 4.9. Looks like we should go to 3 sig figs here. Consistently, you got a time here, or pressure here that's only 2 sig figs. So we're going to go to 4.9 times 10 to the negative fourth. And once again, just like we talked about before, since it's overall first order, that would mean no molarity on the bottom. So inverse seconds would be our rate constant. So remember, if you want to know what your unit is, it's going to be 1 over some molarity, and you take the overall order minus 1 times your time unit. In this case, time unit given was seconds, and since it's first order, 1 minus 1 is 0, so no molarity down there. So that's how we would calculate our rate constant. Now, once we've got the rate constant, just like we talked about before, since we know it's first order, we know that the ln of the concentration at time t is going to equal negative kt plus the y-intercept, which would be the ln of a naught. And if we know everything but one unknown, we can calculate what the final is. Now this one says something different. In C it says what will be the partial pressure of A at 1600 seconds. So in this particular problem, we're going to be given a time. Now, if time is right here, and this is our k value, so we know that, so we can plug k in there. You need to understand that in this particular situation, this is represented by our y-intercept. And the y-intercept in this particular case is going to be given in our original equation, which is given right here. So all we have left is the inverse of our concentration at time t, or the natural log of our concentration at time t. So remember, when you are done, you're not getting our answer, we're getting the natural log of our answer. So we're going to have to take e to that value to fix it and convert into our final value. So remember, we're getting the natural log of what we're looking for. So you set up your equation. Let's see if I can get a little more room here to do this particular calculation. Extend that page a little bit. Okay, so what will be the partial pressure at 1600 seconds? Well, we know that the ln of the pressure we're looking for at time t, and remember time t, 1600 seconds, is going to equal the negative of our k value. Remember, negative k, that would just be slope, so that would be negative 4.915, carrying a few extra significant digits here through to the negative fourth, and that would be inverse seconds, times 1 over t. Well, t is given here. I'm sorry, not 1 over t. Let me erase that. Times t, which would be 1600 seconds, plus our y-intercept, which was 5.82604, carry through a few extra significant digits. And once again, we've got an equation with one unknown. Calculate this out and find out what the ln of p equals. Take e to that value. Remember, to get rid of natural log, we have to take it e to that value, and we'll end up solving for p. We end up with a pressure of 154, and our units of pressure up here are millimeters of mercury. So at that particular time, that would be our overall pressure. Once again, it never hurts to double check. 1600, going to fall between those two. Does my pressure fall between those two? Yes, it does. So remember, when you do the calculation here, you're going to get the natural log of p. You have to take e to the natural log of p to solve for p. So that would be the second problem. Now looking at problem 3, this one's a little bit different. You'll notice they give us some specific information here that makes this problem a little bit easier than the ones we've looked at in the previous ones. The catalyzed decomposition of hydrogen peroxide, H2O2, is represented by the following equation. This is a reaction you should know. Hydrogen peroxide breaks apart into water and oxygen gas. Now, the kinetics of the decomposition reaction were studied, and the analysis results showed that the reaction was a first-order reaction. So they're telling us the order in this case, which things should be clicking inside your head what exactly that means. Now, some of the experimental data are shown below. So we've got concentration, time, data. So since we know it's first order, concentration versus time would not be linear. Since it's first order, we know it would be the natural log versus time that's linear. So keep that in mind when we approach the problem. Now, during the analysis, the data, the graph below was produced. So they have a graph here. Notice the axis, the y-axis at this point is not labeled. And that's actually the first thing they ask you to do, label the vertical axis. Well, remember, what would be linear, and this is showing a linear relationship, would be the natural log of the concentration. So that has to be my y-axis. Second question, what are the units of the rate constant? We just looked at this. Remember, units are related to the order. If the overall order is first order, then that means my units have to be inverse time. So my value for K, inverse, and notice my time units are minutes. So I know it's going to be inverse minutes. So 1/minutes would be my units for the value of K. Then the last question on the graph, draw the line that represents the plot of the uncatalyzed first order decomposition. Now if this is catalyzed, remember it's going to have a faster rate. That means a steeper slope. So for the same change in X, more change in Y. So if I have an uncatalyzed reaction, it's still going to be first order, so the ln of time is still going to be linear, but it's not going to be happening as fast. So that line, which is not as steep, so it's going to have represent basically a slow reaction. That line might represent what the N-catalyzed first order decomposition would look like. Now, it says at 1.0 molar, so notice I'm starting at the same spot I started at before because that would represent the natural log of 1.0 there. So I start at that same spot, it's going to have the same y-intercept, same initial concentration, but now it's going to happen slower. So I'm not going to have as steep as a slope. So that means basically my K value is going to be smaller, so my rate's going to be smaller. So that would be how you answer these questions. Good luck. I will see you in class.